We're talking about actually running the ordination in R. Here's an example of an ordination here on the screen where we have an ordination that's run, in this case for my lawn experiment. And so we can see it all pretty and displayed in a graph. But what we want to do is see how this actually runs, and especially we want to see how stress is computed. In order to do this, I had to make sure that both my COM data and my environmental data are loaded, and then I had to make sure two packages were running. I did library vegan, library ecodist. After that, I'm ready to set my distance to a city block distance or a Bray-Curtis distance. Let's do a scree plot of our NMDS with different numbers of axes. Now remember that there are different ways to do this. We're starting with as many dimensions as we have species, and we're trying to compress this ordination down to 2 dimensions. We could compress it all the way down to 1 dimension where it would just be a line with a score. I'm going to ask you to do this command where we take we do an NMDS. Of some distance measures that we created using the Bray-Curtis distance. I'm going to plot stress by number of axes. If you have any trouble with this, it's possible that the quotation marks are being recorded differently, and so occasionally you may have to retype some of this code. So if you run into each trouble, just try that. Try going back and making sure that all the text is recognized. So what does this plot say? Let's take a close look at what we just did here, because we got kind of a weird looking plot. So in this plot here, what you're looking at is at the very top, you have the stress when you have only one axis. And so that's a unidimensional solution to the ordination. We've compressed all the information from all our species into just a single score of community relatedness or community distance. And you can see there's a lot of stress. We've got a stress of 0.4 in this case, which suggests we've lost a lot of information in compressing it to one axis. What we generally look for in an ordination is a place where we have an elbow or a big decrease in stress with a single increase in axes. So when we go from 1 to 2 axes, notice that we have a huge drop in the amount of stress, and then there's kind of a plateauing as we go between 3, 4, and 5 axes. So in general, this is a good indication that a 2-axis solution is fine. In general, we're looking for stress less than 0.2, and we have that here. So that is our stress. Next, we're going to actually run our ordination. And in order to actually run our ordination, we're going to first set a seed. And why we're doing that is that the ordination is an iterative process. It's going and it's repeatedly trying to find a solution, compressing the axes and measuring the stress. And because of that, there's a randomization procedure that's taking place in the background. And we want to be able to repeat the exact same ordination. Otherwise, if we don't have the same starting place, we'll always end up at a slightly different ending location. So I'm going to set my seed at 1001. That could be any number you want. I just chose 1001. And then I'm going to do my actual NMDS with this command here. m.mds is going to be the name of my ordination. The command is meta MDS using the dataset COM, and I'm going to do 100 iterations until I get the lowest stress. Okay, you'll see that this continued to run. It ran over and over and over again looking for a best solution, and ultimately it found a best solution for me, and we have that ordination now ready. And we can look, the next thing we can do is look at a stress plot of our final ordination. Let's take a look at that. Okay, so I really like these plots. This is really nice. It's showing me the observed dissimilarity, that is the actual dissimilarity mathematically between my individual plots, and the ordination distance. So how far apart points are in the ordination versus how far apart they are in reality in terms of shared each individual species. So for each individual species, you can see how far apart each plot is. You can combine that for all species in the data set, and mathematically you can calculate the dissimilarity. In ordination distance, remember, we've compressed all that information to 2 dimensions, and we're going to look to see how close the ordination distance, the distance on the graph, is to the mathematical distance in reality. So this is showing us that relationship, and you can see it's a pretty good fit here. We've got somewhere between 99, well, it's somewhere around 99, 98% of our variation is explained by a fit of the data, especially a linear fit of the data. And so there's a close agreement, observed dissimilarity and ordination distance. When I type in the command just m.mds, that's my ordination, I get my actual stress associated with the ordination. You can see that it was 0.066 in 2 dimensions. This was found a convergent solution after only 20 tries. It would have gone up to 100, but it was finding consistency, and so it stopped. And so this is a really nice ordination. It's a really low stress. It's really easy to represent in just 2 dimensions. And so the only thing left to do is go ahead and start ordinating that data and seeing what it actually looks like as a graph. There's our data, and sites 1 through 6 here were my wet site locations, and sites 7 through 12 were my dry site locations. You can see they're splitting off pretty easily in the screen, and the next thing we've got to do is start creating a graph where we can actually display what plot type or what site type is represented where on the graph.